So take a look at this graph over here in blue. And suppose this is a temperature graph, okay? So that in blue is a temperature graph for any particular point xy. That point gets mapped up to a certain temperature. Okay, you can think about this as, say, a map of a campus, for example. And at each point in the campus, you get a particular temperature. Okay? Now, we talked about how to discuss derivatives in that setting, right? You don't get just one simple derivative. You have partial derivatives, the changes along the x that's uh, uh, encoded with using the f sub x, right? Partial derivative with respect to x. And you have the changes along y, which were given by the partial derivatives with respect to y. Now, that's just for the temperature, okay? Now, suppose we add an extra complication, right? That we're traveling along a particular path in green in the xy plane. So one is perhaps traveling around campus, and this is the path that they leave. Okay, it could also be seen here on the xy plane. The path lives on the xy plane, and we choose to track our path using time. Okay, so this r gives us a particular position at a particular time, which then using the function t gives us a temperature as we move along in time. Okay, so now temperature implicitly depends on time. Okay, it explicitly depends on the point that you're at, but implicitly depends on time. Why? Because, well, you're traveling using the time axis. Okay, you're mapping out your path using time. And now here's the question that we could ask. We could ask for this person who's taking this path as they move along this time, okay, so that they're traveling along here. What is the rate of change of temperature for them? I mean, they are traveling around campus, so some places are a little hotter, like up here, than other places down here or down here. So we could ask for this person who's taking this particular path as they travel through time, okay, how does the temperature change? What is the rate of change of temperature with respect to time? For that, we're going to need the chain rule. Okay? The chain rule gives us the derivative of this function z, which you could think about as the temperature in that particular example, but more generally, z is a function of xy, and we want its derivative with respect to t, which in this example was the time, but in general is just some parameter t. X and y, which the function z explicitly depends on, x and y explicitly depend on t, and hence z implicitly depends on t as well. Okay, so what's the derivative of z with respect to t? Okay, we know about the partial derivatives. We already discussed that. But now we want the derivative with respect to t as we move along the path x of t, y of t. Well, for that, we have this formula here. You take the partial derivative with respect to x of z, and you plug in the path, and you multiply that by the derivative of x with respect to t, and likewise for y. Okay, I wrote this all out explicitly to emphasize plugging in the path into your partial derivative with respect to x there of z, but you'll often see this written this way. Okay, but here, once you take partial derivatives, don't forget you have to plug in the path. So let's take a look at a concrete example and use this formula. Okay, so we have this function of two variables z that depends on x and y, and here's its how it looks. You have x squared minus 3y squared plus 20. We also have we're taking a particular path. This path is given by x of t equal to 2 cosine t and y of t equal to 2 sine t. Now we want the rate of change with respect to t of z, given that we're walking along that path. Okay, and here I'm saying path and walking, of course, as just an analogy. So we want to find dz dt, and we want to find it at t equals pi over 4. Well, let's just use the formula. So we're going to need partial z partial x. That's that. We're also going to need partial z partial y. That's what you see there. We have also dx dt. So we're going to take the derivative of x with respect to t, and dy dt. And we're going to take the derivative of y with respect to t. We get 2 cosine t. And here, for example, partial z partial y gave you the negative 6y. You just treat x as a constant. So plugging these into our formula that you see here, we get this. But do not forget to plug in x of t and y of t into the partial derivatives. And when you do that, you get this relation here, which simplifies to minus 16 sine 2t, or negative 32 sine 2t cosine t. And so this is the partial derivative. This is the derivative of z with respect to t at an arbitrary t. We would like it at t equals pi over 4. And so what do? You just take that and you plug in pi over 4, and you get minus 16. Okay? Now, this remark down here is telling you that we could have done this problem a different way. Instead, we could have plugged in the path. Okay? So we could have just plugged in z of r of t. Okay? Where r of t, of course, is given with this x of t and y of t. So you could have had z of r of t is going to be x of t squared minus 3y of t squared plus 20. And then we could just take this guy and plug it in for y of t, and take this guy and plug it in for x of t. And then we would be left with a function that only depends on t. Okay? So what you're seeing there is a function that depends just on t, right? It's the z value that you would get as you travel along the path with t given there, okay? Well, what you could have done is plugged in the function first and then taken the derivative. Now take the derivative with respect to t. You will get the same answer that you got over here. But it's useful to talk about this concept more generally rather than always just taking in the path and plugging it in. So what the chain rule allows us to do is to compute this thing with conceptually understanding the path being different than the function. Okay, so what happens when you plug in an arbitrary path? We could always take particular paths and plug them in, but the chain rule allows us to talk about arbitrary paths.